In our lesson today, we are going to do a thorough discussion of radioactivity. Now, this is my favorite topic out of all the topics in the chemistry syllabus. It's short and sweet, and this is something that I believe a lot of students wish chemistry topics could be. I hear you. So, coming back to radioactivity, the content that is discussed in this topic is quite different from what you are used to. But before I get into the discussion of radioactivity, there are a few things that I need to remind you of. These are things that are crucial to your understanding of this topic. Number one, the structure of the atom. Now, this is something that was introduced in Form 2. So, let us just remind ourselves. An atom is the smallest particle of an element that takes part in chemical reactions. So in atoms, you're going to have electrons that are placed in orbitals, in energy levels, and these are negatively charged particles. Within the nucleus of the atom, you're going to have two particles, neutrons that are neutral, they have no charge whatsoever, and protons that are positively charged. Now, the number of protons is always equal to the number of electrons in any atom. But the number of neutrons can either be equal to that of protons or greater, with the exception of hydrogen. Now, let me give an example of chlorine. So, chlorine has the atomic number of 17. That means it has 17 protons and will therefore have 17 electrons. So, how many neutrons does it have? Now, you're going to have some chlorine atoms having 18 neutrons and others having 20 neutrons. Okay, so they have a difference in the number of neutrons. Are we still talking about the same element? Of course, because it's the protons that determine the identity of the element. As long as we're having the same number of protons, which in this case is 17, we are still talking about chlorine. But because we have a difference in the number of neutrons, we need to have, something to label these two. And that is where isotopes come in. So isotopes are atoms of the same element that have the same number of protons and electrons, of course, but a different number of neutrons. So by this definition, chlorine has two isotopes, and this is how they are illustrated. So in this case, the subscript, the one at the bottom, illustrates the atomic number, the number of protons. So you have 17 for both atoms. Now the superscript, the one at the top, illustrates the mass number. So this is the number of protons plus neutrons. So in the case of chlorine 35, how many neutrons do we have? 18. How did we get 18? 35 minus 17. In the case of chlorine 37, we have 20 neutrons, 37 minus 17. So those are the two isotopes of chlorine. Now this is something that I would like you to bear in mind because radioactive isotopes are something that I will discuss later on. Now in chemistry, most reactions involve electrons, specifically the valence electrons, the electrons that occupy the outermost energy level. So when chemical reactions take place, atoms lose electrons, gain them, or maybe share them. But when these reactions take place, the protons and the neutrons are not affected kabisa. The numbers of neutrons and protons do not change. However, there is a different type of reaction called nuclear reaction that involves changes in the number of protons and neutrons. These are what you're going to discuss in this chapter. Now, one other thing I would like to mention before we proceed is the stability of nuclides. So when we talk about the nuclei of atoms, some are stable while others are not. What determines which nucleus is going to be stable and which is not? The ratio of neutrons to protons. Okay, let's take an example of calcium. Calcium has 20 protons and 20 neutrons. This is a ratio of 1:1, which is very good. So if you have atoms where you are going to have the ratio of protons to neutrons as 1:1, these are atoms whose nucleus is going to be very stable and it does not undergo any change. It remains intact. But if you have atoms whereby you're going to have a larger number of neutrons as compared to protons, this is going to be an atom whose nucleus is unstable. Okay, let me give an example of thorium. So we have an element called thorium. Now, as you can see from this, it has an atomic number of 90, therefore 90 protons. How many neutrons does it have? 144 neutrons. Just look at that. quite a big difference. So such nuclei are going to be unstable. If they are unstable, what happens next? They are going to spontaneously disintegrate, break down. This process is spontaneous, it happens randomly, and they break down in order to become stable by forming smaller nuclei. This process is accompanied by the emission of particles and energy. So when we talk about radiation, there are three main types of radiations. We have alpha radiation, beta radiation, and gamma rays. So depending on the nature of the nuclide, you can have one of these three happening or even a combination of two. Maybe alpha radiation and gamma rays occurring at the same time. Now, I'm going to discuss each of these three types of radiations. So let's start with alpha radiation. Now, alpha radiation occurs when an alpha particle is emitted. Now, an alpha particle is a positively charged particle that contains two neutrons and two protons. So there we have it. So over here, because we have two neutrons, the atomic number is going to be 2. And because we have two neutrons, the mass number is going to be 4, 2 plus 2. Now, this particle is positively charged because it has no electrons. So if it has no electrons and it has two protons, that means it's going to have an overall charge of plus 2. Now, when an atom emits an alpha particle, what's going to happen is that its atomic number is going to decrease by 2, while its mass number decreases by 4. Okay, let me explain that. So you're having the parent nucleus undergoing radioactivity, leading to the formation of the daughter nuclide. So in this case, with the parent, what will happen is that when it undergoes alpha radiation, it emits an alpha particle that contains two neutrons and two electrons. That means whatever remains is what forms the daughter nuclide, and that is going to have two protons and two neutrons less. Where did these go to? To the alpha particle. So for example, let's imagine we have uranium. This is uranium. It has an atomic number of 92. So 92 protons. It has a mass number of 238. So that is the sum of the neutrons and the protons. Now, when uranium undergoes alpha radiation, it's going to emit an alpha particle that contains two neutrons and two protons. So whatever remains in the uranium atom after the emission of the alpha particle is what is going to form the new element, which is thorium. So how many protons will thorium have? 92 minus 2, giving us 90. What about the mass number? The mass number is going to decrease by 4 because uranium loses two neutrons and two protons. So we are going to have a mass number of 234, and this gives us thorium. Now, whenever alpha radiation takes place, you end up having a new element. So this is no longer uranium because this element has a totally different atomic number than uranium. Remember when you talked about protons, protons make up the identity of an element. So if you have an element that has two protons less than its parent, that is no longer the same element, it's a totally different one. Moving on to the beta particles. So beta particles are negatively charged particles. They have a negative charge of 1. Now these are actually considered to be electrons. Now whenever we discuss electrons, we usually talk about electrons present within energy levels. But in this case, you will find that the beta particles do not originate in the energy levels. No, that is not where they come from. They actually come from the nucleus, schizene. So what happens is that in the nucleus, you have the neutrons and the protons. Now, when beta radiation takes place, one of the neutrons is going to undergo a change. So it changes to form a proton and an electron. Now, it's actually this electron that is emitted from the nucleus, forming the beta particle. How cool is this, by the way? So a neutron changes to a proton and an electron. The proton remains within the nucleus, but the electron is emitted, and this is going to be in form of the beta particle. Now, this has a negative charge of 1. So that does not actually represent the atomic number. It represents the charge of this particle. Now, when it comes to the beta radiation, what happens is that it changes the atomic number but does not have any effect on the mass number. So let's start. The neutron converted to a proton and electron. So we are going to have one additional proton. That means the atomic number will increase by 1. What about the mass number? The mass number will not change at all. Remember, the mass number is the sum of neutrons and protons. So what we're having in this case, we are having just a neutron changing into a proton. So the number of neutron decreases by 1, but the number of proton increases by 1. And at the end of it, you are going to have the same thing. So the mass number does not change. Okay, let me give an example to put this into context. Let's say we have carbon 14 over there. So this has 6 protons, and as you can clearly see from this example, and 8 neutrons. So the mass number is 14, 8 plus 6. Now when it undergoes beta radiation, it leads to the formation of nitrogen 14. So since this is beta radiation, you're going to have an increase in the number of protons. Why? Because the neutron changes to a proton. So you're going to have an increase in the number of protons by 1. So it increases from 6 to 7. What happens to the mass number? Okay, let's go through it. So we're talking about the neutron changing to a proton. So initially we had 8 neutrons and how many protons? 6, giving us a total of 14. Now after the radiation, what happens is that the number of neutrons decreases to 7, but the number of protons increases to 7. So at the end of it, we end up having a total of 14. So again, no change. And this is beta radiation. Moving on to the last one, the gamma rays. Now, gamma rays consist of electromagnetic waves. They have no mass and no charge. So they have no effect whatsoever on the mass number and atomic number. And this is how they are represented. So this brings us to the end of this lesson. In our next lesson, I'm going to do several examples of nuclear reactions to put this into better perspective for you. I hope to see you there.